A very good morning. Welcome to the session. So today's session is on Gaussian random variable. So this week I was taking a series of classes on random variables. So this is the fourth session. In the last three sessions, I've talked about probability density function. In the second session, I've talked about cumulative distribution function. And in the third session, I've talked about moments of a random variable. So now this is the fourth session. In fourth session, I'm talking about Gaussian random variable. So in a similar manner, in tomorrow's session, I'll be talking about exponential distribution and uniform distribution, the intricacies in those distributions. And in the last session, we'll be solving questions based on all the concepts that I've discussed in this week. We'll be solving questions based on that. Okay, so let's start with this today's topic, Gaussian random variable. So Gaussian distribution is one of the most important distributions among random variables. Among the distributions available, Gaussian distribution is the most important, you can say. Why? Why is it most important? Because in most of the practical situations, most of, not all of them, in many of the practical situations, if you plot the distribution or if you see the statistics, the curve fits to be close to Gaussian in many practical situations. So for example, noise in a communication system is random in nature. If it is random, you can plot a PDF for it, probability distribution function for it, probability density function for it. And if you plot the probability density function of noise, it has a shape of exactly Gaussian shape. Okay. So what exactly is Gaussian shape? What is the mathematical equation for it? We'll discuss all those details. We'll discuss a lot of things about Gaussian random variable in today's session. Right. So I've given one example of Gaussian PDF, which is noise in communication system. Not only noise in communication system, there are a hell lot of situations where the distribution turns out to be Gaussian. Okay, I'm not saying that all distributions will be Gaussian. Many distributions are Gaussian in practical situations. But there are situations where the distribution can be uniform. There are situations where the distribution can be exponential. From situation to situation, if you plot the PDF of a random thing, the PDF can have any shape. So generally observed shapes are Gaussian, exponential, uniform, Rayleigh. Okay, these are the binomial, Poisson. These are the distributions that we learn in our mathematics class or in random variables, random process class also. About around 5 to 6 distributions generally we talk about, because in most of the practical situations we observe one of these 6 or 7 distributions. But out of these 6 or 7 distributions, comparatively, this Gaussian distribution will be seen significantly more number of times than the other distributions. Right. So as you can see, my subjects of expertise are communication systems and signals and systems. So this is my Telegram group. So if you wish to ask me any doubts based on communication systems or signals and systems, you can definitely post it in this group. I can help you guys. Okay. Next. So let's get into the topic of Gaussian random variable. So what is the agenda of today's session? So we'll first quickly discuss the questions that I've given you as homework in yesterday's session. Next, I'll talk about what exactly is this Gaussian random variable, what is the equation of it, and how does it look like, and there are many important details that we need to know about Gaussian random variables. Okay. Next, what is the relation between Gaussian random variable and normalized Gaussian random variable? So when I say Gaussian random variable, it can have any mean and any variance. When I say normalized Gaussian random variable, a Gaussian random variable with zero mean and variance is 1 unit, we call it as normalized Gaussian random variable. So these two should have some relation, and what exactly is that relation, we'll talk about it. That's a very important stuff. So which we have to use whenever a question is given on Gaussian random variables. Yes, this relation will be very helpful. Next, there is one more important thing about Gaussian random variables. So there is something called Q function. Q function of Gaussian random variable. We'll talk more details about this Q function. So whenever a question is given based on Gaussian random variables, the answers, the options will be in the form of Q function or capital F function. Capital F function, when I say capital F function, it is cumulative distribution function of Gaussian random variable. So the options will be in the form of Q function or CDF function. So what exactly is this Q function, and what is the relation between Q function and CDF function? We'll talk about those things. Okay. So there are lots of important stuff that we have to understand about Gaussian random variables. Okay, we are gonna go one by one, step by step, so that you can understand things easily. So this session is very important, guys. So you have to focus very carefully. So if there is any slight doubt also, just go through the session once again. It will be very helpful. Right. So let's quickly in the next 5 minutes we'll quickly complete these two questions, and then we'll move on to today's topic, Gaussian random variables. So a discrete random variable x takes values 2, 4, 6, 8 with equal probabilities. Okay. Now the question asked is find the mean square value of the random variable, expectation of x square. This is what they're asking us. So the formula we can write. Actually, I've taught you without formula also. Let's go with the basics. So the probability, there are 4 values here, and since they're all having equal probabilities, what is the probability of all of them? Probability of all of them is 1 by 4, because it is said that they all have equal probabilities. So 2, 4, 6, 8, all of them have same probability, which is 1 by 4. Now, so what do we want to find? We want to find mean of squared value, expectation of x square. So whenever you want to find mean value of x square or expectation of x square, you are just trying to average. We are trying to find a statistical average. So it's a second order moment. We call it as mean square value. So what do we want to average? Expectation means average. We want to average x square values. So what are the possible x square values? 2 square, 4 square, 6 square, and 8 square. These are the possible values for x square. These values we want to average. How do we average? Expectation is nothing but weighted average. What are the weights for 2 square? 2 square happens with the probability of 1 by 4, or the weight of 2 square is 1 by 4. Weight of 4 square is also 1 by 4. Weight of 6 square is also 1 by 4. Weight of 8 square is also 1 by 4. That's it. So whatever they want to average, whatever they want to average, take the possible values for that. So x square they want to average. So x square is not a single value. The possible values for x square are 2 square, 4 square, 6 square, and 8 square. So the possible values for x square, you take them and multiply them with their corresponding weights or probabilities. So, or if you want to go with the formulas, that is fine. Sigma x square into fx of x dx, fx of x, where x runs from minus infinity to plus infinity. So you're saying minus infinity to plus infinity, but you're taking only from 2, 4, 6, 8 only. Yes, correct. Basically, random variable takes all real values, but so it takes these real values with non-zero probabilities, and it takes other values with the 0 probabilities. For example, 3 square it takes with 0 probability, 3.1 square it takes with 0 probability. So you can take all the values, 2 square, 2.1 square, 2.2 square, 2.3 square, all of them, and multiply them with their corresponding weights, which is 0. So you don't need to take the remaining values. Okay. Right. A continuous random variable x takes values 2 to 8 with equal probabilities. Yeah, expectation of x square, we got it. Let us quickly find the final answer. So 2 square plus 4 square, 4 plus 16 is 20, 20 plus 36 is 56, 56 plus this is 64, right? 56 plus 64 is 60 plus 60, 120, 120 divided by 4 is 30. Is that okay? I think that should be correct. 16 plus 4, 20, 20 plus 36 is 56, 56 plus 64 is 120. Yes, 120 divided by 4 is 30. I think you are also getting the same answer. Right, so first question is done. Second question, second homework question. So a continuous random variable x takes values from 2 to 8 with equal probabilities. So they're saying continuous random variable, it takes values from 2 to 8. How many values are there between 2 to 8? There are infinite values between 2 to 8. Okay. So let us plot the PDF. Since it is continuous random variable, they're saying all the values are having equal probability, which means they're saying it is a uniform distribution. They're saying it is a uniform distribution. They can also ask the question in a different way. They can say a continuous random variable x is uniform, or a continuous random variable is having a uniform distribution. Instead of saying this sentence with equal probabilities, they can also say that this random variable x is having a uniform distribution, or it's a uniform random variable. They can use different sentences. They all mean the same thing. Right. So this is the PDF information that is given. From the information given, I've plotted this. So could you tell me what is the height of this PDF? Height of this PDF is, the width is 6 units. So if the height is 1 by 6, if the height is 1 by 6, then only the area will be 1, right? So this is the PDF. Now they're asking us to find the mean square value. So to find the mean square value, expectation of x square is equal to, since it is continuous PDF, the formula turns out to be x square you want to average. When you want to average, what should we do? You have to multiply them with corresponding probabilities and then just add them up. Because it is continuous random variable, summation will not work out, so we have to do integration. For discrete random variable, it is summation. For continuous random variable, it is integration. So to resolve this, to solve this one, you have to know the equation of this. Fx of x equation is 1 by 6 for values of x between 2 and 8. 2 less than x less than 8. And its equation is 0 for all the remaining values of x. So integrate x square. What is the equation of fx of x? It is 1 by 6. That equation 1 by 6 for fx of x is valid only from 2 to 8, limits from 2 to 8. Only for values of x between 2 to 8, this equation is valid. And for the remaining values, the equation of fx of x is 0. So the next term is from 8 to infinity or minus infinity to 2. The equation of fx of x is 0. So you don't need to consider that. Next, what is this? So 1 by 6 outside. Integration of x square is x cube divided by 3. Limits from 2 to 8. So it turns out to be 1 by 6 3s are 18. Limits if you substitute 8 cube. 8 cube minus 2 cube. 8 cube minus 2 cube. 8 is 64. 64 into 8. How much is that? 8 4 is 32. 8 6 is 48. 48 plus 3 is 51. 512. Right? Okay, 2 power 9 is 512. Yeah. 512, if you remove 2 cube, which is 8. 512, if you remove 8, it will become 504, right? 504 divided by 18. So can we cancel something here? Yes, I think we can cancel something. 6 will go, right? 6 3s, 6 8s of 48. 6 8s of 48, 24. 6 4s of 24. 84. 84, will it be divided by 3? I think it will be divided by 3. So it is 3 2s of 6. 3 8s of 24, right? 28. I think that should be fine. Yeah, perfect. 28 should be correct. Are you getting anything different? I believe I have done it correctly. There are no calculation mistakes, I guess. 3 is 18. 8 cube minus 2 cube. Okay, 540. Perfect. That should be correct. Right. So with that, we are done with the homework questions. Let's move on to the next slide, which is today's topic, Gaussian random variable, my favorite topic. So why is my favorite topic is because there are a lot of beautiful observation in this Gaussian random variable. There are beautiful observations. Let's observe the things that we need to observe one by one. Okay. So we can also call this distribution as a normal distribution also. Gaussian distribution or normal distribution, both are same. Gaussian, they also call it as normal distribution or Gaussian distribution. Okay, when I say Gaussian distribution, it represents PDF, not CDF. Okay, so PDF means probability density function. We call it as density function, but in general practice they call it as distribution, normal distribution, Gaussian distribution. But actually, Gaussian distribution is a PDF. It does not represent a CDF. Okay, it always, because Gaussian distribution, if you observe, the shape is like increasing and then decreasing. So CDF can never be decreasing. It should be monotonically non-decreasing. So Gaussian distribution or normal distribution represents a PDF. It represents only a PDF, probability density function, not CDF. Okay, but this Gaussian distribution, you can plot CDF for it. You can plot CDF for it, but Gaussian shape represents only PDF, not CDF, because Gaussian shape can never represent CDF because it is decreasing also. It is increasing as well as decreasing. So Gaussian shape looks like this, right? CDF can never be decreasing, no. So Gaussian shape can never represent a cumulative distribution function. It can only represent a probability density function. Okay. So Always, whenever you see a Gaussian shape, will it represent a PDF? No, right? Whenever you see a Gaussian shape, that does not mean that it always represents a PDF. Gaussian shape can represent anything, right? It need not represent only PDF, it can represent many things. But it will represent PDF, it will if it satisfies the properties of PDF. What are the properties of PDF? The PDF should be having, the function should be having only positive value, and the area of the function should be equal to 1. That is, they are the two properties of probability density function. So if this Gaussian shape has an area of 1, then this Gaussian shape represents a PDF. If the area is not 1, then it will not represent a PDF. Okay, right? So the notation for generally the notation for normal distribution is something like this. N represents normal distribution of, there are two parameters given here. First parameter represents mean value. For a random variable x bar is the notation that we use for mean value, and the next part is variance. This is the notation that is followed. If somebody says n of 4 comma 5, what that means is this only the information about Gaussian distribution. There are only two important informations about Gaussian distribution. One is mean value, second part is variance. If you know mean and variance, then you can find every detail about Gaussian distribution. Only these two parameters are sufficient to understand everything about Gaussian distribution. So that's why these, so let's say somebody tells a Gaussian distribution is given like this: n of 4 comma 5. N means normal distribution. It has a mean of 4 and a variance of 5. Yes, with this information we can find any question based on this Gaussian distribution. Yes, we can. Right, now let us get into the details of it. Okay, so how does the shape of it looks like? Let me plot the shape. It's a decreasing shape on both sides. As a function of x, this represents PDF. So the y-axis can be anywhere. Okay, I'm plotting a general Gaussian function. Better I plot it. See this one, this is a decreasing function. When will it go to 0? At x equal to infinity only it goes to 0. As x tends to infinity, this Gaussian function tends to 0. See this one on the other side also. As x tends to minus infinity, it tends to 0. It keeps on decreasing. It goes to 0 only at infinite, after infinite value of x. Right. So this center point with respect to which, see this line? This line, with respect to this line, this shape is symmetric. Gaussian shape is a symmetric shape only with respect to its mean value. This value is the mean value of the Gaussian function. With respect to its mean value, it is symmetric. With respect to its mean value, it is symmetric. What is the equation of that vertical line? Let me draw the equation of that, tell you the equation of this vertical line. The equation of this vertical line is, if you talk in terms of mathematics language, y equal to x bar, or if x bar is 5, x equal to 5, sorry, y equal to 5, my mistake. It's not y equal to 5, my mistake. It is x equal to x bar. This line represents x equal to x bar is the equation of this line. Because see this one, at every point on this line, x coordinate is x bar only. Correct? So with respect to x equal to x bar line, this Gaussian PDF is symmetric. Gaussian PDF is always symmetric with respect to its mean value. It is always symmetric with respect to its mean value. So if you know mean value, then you'll know how to plot it. Correct or not? If you know mean value, take that mean value, You know the shape of the Gaussian function. So place the midpoint of this Gaussian function at this point, whatever is the mean value. Or if you know the Gaussian function, observe with respect to which point it is symmetric, that point will be the mean value. Very easy. Whenever a Gaussian shape is plotted, it is easy to figure out the mean value. Or if you know the mean value, you can plot the Gaussian function. Okay, only mean value is not sufficient to plot the Gaussian function. Mean value only represents the center point of it. But the width of the Gaussian can be anything, no? So I have plotted with certain width, okay? So this width can be anything. So finally, Gaussian shape is some kind of decreasing shape on both sides. But how fastly it decreases, okay, it depends on the variance. Variance represents the rate at which it decreases on both sides. Okay. For example, so what is the equation for it? Let me first draw the equation, write the equation for it. Let me write the notation for this as small fx of x. Generally we use small f for denoting PDF. So what is the equation for it? So the general mathematical equation given for this curve, which we call it as Gaussian function or normal function, is 1 by root of 2 pi sigma square. You might have learned this in many places. Mathematics you might have learned, in communications you might have learned. 1 by root of 2 pi sigma square, where sigma square represents variance, into e to the power of minus of x minus x bar whole square divided by 2 sigma square. See this one? So this is the equation valid for all values of x. From minus infinity to plus infinity, this equation is valid. See this one? In the power, there is a negative sign. Because there is a negative sign, that's why you observe, as x increases above x bar, what happens? This value increases, but there is a minus sign in the power. As the value increases in the power with the negative sign, what happens? It decreases. As this increases with the negative sign in the power, what happens? It decreases. Similarly, as x decreases from x bar, from x bar, there is a square term here. Because there is a square, as x decreases from x bar, this value is negative, but squaring is done. Because of that, this negative will become positive, but overall there is a negative sign. The magnitude of this one increases as you go far from x bar. As you go far from x bar on this direction or in this direction, this power increases, but with a negative sign. So that's why it decreases on both sides. If this was a positive sign, then this would not be the shape. The shape would be something like this. It would be increasing shape on both sides. Because of this minus only, it is decreasing shape on both sides. Okay. So this is the equation of a Gaussian PDF. Okay. See, Gaussian shape means it should have something like this. Okay. When I say Gaussian shape, when anybody says Gaussian shape, or when you see some equation, how to figure out if it's having a Gaussian shape or not. Gaussian shape need not represent only PDF. It can represent any other thing. Gaussian can be the shape of some pulse. Gaussian can be the shape of some curve. So it need not be the shape of only PDF. It can be the shape of PDF, but it can also be the shape of some other thing also. For example, in GSM, if you remember, global system for mobile, it's a 2G technology, 2.5G technology. In this, we use something called GMSK technique. The modulation technique that we use is GMSK. We call it as Gaussian minimum shift gain. Gaussian minimum shift gain. So that is the modulation technique that we use. Why is it called as Gaussian minimum shift gain? Because the pulse that is used for transmission of 1 bit or 0 bit is a Gaussian pulse. It is a Gaussian pulse. They use Gaussian pulses. For 0-bit transmission, they use a Gaussian pulse only, but a negative Gaussian pulse. Something like this. So Gaussian pulse. So Gaussian can be the shape of a pulse. Gaussian can be the shape of a PDF. Gaussian can be the shape of anything else also. So how to figure out Gaussian shape mathematically? Okay, so if equation is of the form e to the power of minus of variable square. If variable is not square, then it will become exponential function. The variable should be squared. If the variable is y, it is e power minus y square. If the variable is x, it is e power minus x square. Okay, so if it is of this form, some constant, and you can have a constant also, that constants will not change the shape, overall shape. I mean, Gaussian shape will not become some other shape because of some constant. See this one? Examples. I'll give you some examples. E to the power of minus y square. See this one? In the power, minus sign should be. If there is no minus sign, what happens? It will not be decreasing both sides. And the variable should be squared. If the variable is not square, it will be an exponential function. It will be like exponentially decreasing or increasing. Right. Some other examples, e power minus 4z square. See this one? E power minus p square divided by 4 if p is the variable. Based on what is the variable. If p is not a variable, then if p is a constant, this total thing is a constant. This will not be a curve. If p is a variable, then this represents a Gaussian shape. Okay, next e power minus of y minus 5 whole square. See this? Variable whole square. Variable, if you subtract it with some value, what happens? The location of the Gaussian function will be shifted. Because of this, if y is replaced with y minus 5, what happens is, it is like shifting towards right side. The same shape is shifted towards right side. Similarly, e power minus of z minus 6 whole square divided by 4, something like this. Variable can be subtracted with a constant or divided with some constant, that's fine. Okay, so variable finally should be squared. If variable is squared and with a negative sign in the power, that is what represents a Gaussian shape. Okay, right. So there are some beautiful things, beautiful observations about Gaussian. Apart from Gaussian PDF, there are other observations that I'm talking about in this slide. So if you take Fourier transform of Gaussian, Fourier transform of Gaussian is also Gaussian. So I'll write some example also because it's very important stuff here. E power minus 80 square if you take. See this one, variable in time domain, variable is t square. If it is done, the minus sign is there in the power, so it represents definitely Gaussian shape. So Gaussian shaped time domain signal. So if you take Fourier transform of this, there is an exact formula for this. You can remember this. It is root of pi by a into e power minus omega square divided by 4. You can also write this as root of pi by a into replace omega with 2 pi. 2 pi whole square is 4 pi square f square. 4 pi square f square. So 4 gets cancelled. E power minus f square divided by pi f square. Pi square f square divided by a. See this? When you replace omega with 2 pi f, so it becomes 4 pi square f square. 4 gets cancelled. It becomes pi square f square by a. So this is this you can remember. Okay, you can't. It's difficult to derive this one. But using the properties of Fourier transform, you can get this easily only. But by basic mathematical Fourier transform formula, if you use, it will be tough to get this. Yeah, this you can remember. It's easy, more easy. So Fourier transform Gaussian is Gaussian, and addition of two Gaussians is also Gaussian. If you add two Gaussian pulses, the resultant shape also will be Gaussian, but provided their mean values are same. Otherwise, it will have some odd shape, right? Addition of two Gaussians will be Gaussian. Multiplication of two Gaussians will be Gaussian, provided they have same mean value. See this one? If you multiply e power minus y square and e power minus y square again, it becomes e power minus 2y square. E power minus 2y square also has the shape of Gaussian, right? So adding two Gaussians with same center, multiplying two Gaussians with same center definitely will result in Gaussian shape. Okay, so similarly, okay, yeah. So these are the some observations about some Gaussians, any Gaussian shape. So let's get back to our discussion on Gaussian PDF. What is the difference between Gaussian pulse and Gaussian PDF? See, all these are Gaussian shapes, but the area of them, if you calculate the area of them, it need not be 1. If you calculate the area of them, it need not be 1. So it can be anything. But when you are saying PDF, the basic property of PDF is area of the PDF should be 1, right? So any Gaussian shape whose area is 1, we can say that it is representing some kind of PDF. Okay, Gaussian shape, if it is having area as 1, only then it can be called as probability density function. Okay, Gaussian shape does not mean that it is Gaussian PDF. Gaussian shape with an area of 1 unit, that is when we can call it as Gaussian PDF. See this one, only this part. From this, looking at this part, we can say that okay, this is having a shape of Gaussian. And why is this constant that is we are multiplying? Because this constant is multiplied to make sure that the area is 1. This constant is multiplied to make sure that the area is 1. Okay, without this constant, its area can be anything. Its area is not 1. Okay. Okay, good. Next, so this is the mathematical equation for this Gaussian PDF. Next, let's observe some more details. Okay, right, see this one, observe carefully. I'm drawing a line here. Let's assume this is sigma. Sigma square is there, no? Sigma square is variance, sigma is standard deviation. At a point, sigma from the mean, which is x bar plus sigma, and at a point, sigma from the mean on the other side, it is x bar minus sigma. See this one? So if you observe, this area is very, very important. This area, this total area, how much is this? This is 68%. 68% of the total area. Total area is 1. So this part of the area is 0.68. This part of the area is 0.68. Mind this, observe this carefully. In many practical situations, this point will be very handy for you. 0.68 is the area covered within 1 standard deviation on both sides. So within 1 standard deviation on both sides, the percentage of area covered is 0.68. Next, similarly at the same distance again, after sigma, like, so it is at x bar plus 2 sigma, and on the other side also x bar minus 2 sigma. See this? This total area is, how much is that? It is 95% or 0.95. So within 2 standard deviations from the mean, 95% of the area is covered. So only this part of the area is only 5%, which means this part is 2.5%, and this is another 2.5%. So let's go ahead and look at one more thing. After one more standard deviation, it is x bar plus 3 sigma, and one more x bar minus 3 sigma. So this total area, this red, from x bar minus 3 sigma to x bar plus 3 sigma, this total area is 0.99, or 99% of the area is covered from x bar minus 3 sigma to x bar plus 3 sigma. The meaning of this is, from the mean, if you travel 3 standard deviations on this side and 3 standard deviations on this side, 99% of the statistics are covered in that. 99% of the area is covered in that. Okay, right. So let us write whatever information I've given you. This is a very practical information. Practically, it is used in lots of places. If you take not only engineering students, so like other statistical guys, or chartered accountants, or other professions, in many other professions also. So this normal distribution is a very common thing, not only in ECE, in electronics and communications, in other branches, mechanical, civil engineering, in many other branches also. This normal distribution is a very common stuff. And the important details in this, that is what I'm discussing in today's session. So these details are like important in every sector. So in other branches of engineering or in other professions also, this is a very important stuff. Right. So what is the meaning of this? Whatever I've written here, let me write the meaning of it. So probability that random variable varies between x bar minus sigma to x bar plus sigma. What is the probability that, if it is a Gaussian random variable, what is the probability that random variable from the mean value, it can take any value between 1 standard deviation on both sides. Within 1 standard deviations on both sides, random variable can take any value with a certain probability. And how much is that probability? It is 0.68 or 68% of the probability. Next, similarly, the probability that the random variable takes any value within two standard deviations on both sides, is 0.95 x bar minus 2 sigma less than x bar plus 2 sigma. So this area from here to here, if you find the area of this curve, that will turn out to be 0.95. Similarly, if you find the area from this point to this point, it is x bar minus 3 sigma less than x bar plus 3 sigma. Within 3 standard deviations on both sides, most of the area is covered. 99%, which means almost every area, or total area, almost total, not a total, almost everything is covered within 3 standard deviations on both sides. Okay. So from this information, can we find few other informations as well? So let me ask you a few questions. How about x taking a value between x bar and x bar plus sigma? Can you tell me this? Which means I'm asking you to find the area between x bar and x bar plus sigma. I want the probability between x bar and x bar plus sigma, which means this part of the area, only this part of the area. We know this total area is 0.68. Then only this part of the area will be 0.34, right? Half of this total area, because this is symmetric curve. Whatever is the area here from x bar minus sigma to x bar, the same is the area from x bar to x bar plus sigma also. So this area and this area both are equal. And how much is this? 0.34. So this is also same as the area between x bar minus sigma to x bar also, right? Like that, with these details, you can find this part, only this part from x bar plus sigma to x bar plus 2 sigma. What is the area? Yes, we can find that. Only this area we can find, only this area we can find, or combination of these two areas we can find, right? So if the number involved is any of these parameters like x bar or x bar plus sigma or x bar plus 2 sigma, any of these 7 parameters, yes, we can find that area that is involved there with this information. Okay, fine. I hope it is clear till this point whatever I've discussed. So I'm discussing the smaller important details about Gaussian PDF, right? So not only Gaussian PDF, any Gaussian curve has similar characteristics. From x bar minus sigma to x bar plus sigma, 68% of the area is covered. X bar minus 2 sigma to x bar plus 2 sigma, 95% of the area is covered. 95% of the total area. And x bar minus 3 sigma to x bar plus 3 sigma, 99% of the total area of the Gaussian curve is covered. But here we are talking about PDF whose total area is 1. So 95% of total area is 95% of total area as 1 is 0.951. 99% of total area 1 is 0.99. For other Gaussian curves, total area need not be 1. So, but the percentages are same. Any Gaussian curve, it need not represent a PDF, but for them also the same discussion is valid. The percentage of area covered between one standard deviation or two standard deviations or three standard deviation definitely remains the same. Okay, fine, very good. Next. So in this Gaussian curve, we'll talk about a special case. We'll talk about a normalized Gaussian distribution. Normalized Gaussian distribution function. Okay, so what do I mean by normalized Gaussian distribution function? A normal distribution function with a mean of 0 and variance of 1, that is what we call as that is what I mean by normalized Gaussian. A Gaussian distribution function with 0 mean and variance as 1. So let me plot it. On x-axis, x is the variable. Let me plot the Gaussian curve. Same concept, whatever we've discussed previously, same thing is applicable here also. This is a special case of what we have discussed in the previous slide. Hi Parthiban. Good. As a function of x, I've plotted a normalized Gaussian distribution function. So let me represent with f of x, just to show the difference between the previous one and the present one. See this one? I've taken the notation for any Gaussian distribution function as fx of x. For a normalized Gaussian with mean 0 and variance 1, just to show the difference, instead of without subscript I'm taking here. So what is the mean? Mean is 0 and variance is variance sigma square is 1. So in this, mean x bar is 0 and sigma square is 1. Same equation, I'm talking about a special case here. This is the general case. So in this, let us substitute x bar with 0 and sigma square with 1. Now how does the equation look like? It is 1 by root 2 pi into e power minus x square divided by 2. See this? 0 here, 1 here. It becomes minus of x minus 0 whole square divided by 2. Right? X square bit. That's it. That is the equation. So we can observe that the curve is symmetric with respect to 0. So 0 is the mean here. You can observe that 0 is the mean. Whatever is the mean with respect to mean, the curve will be symmetric. Gaussian curve will be always symmetric with respect to its mean value. And based on the variance, since variance is 1 unit, if you travel 1 unit on both sides from the mean, if you go 1 standard deviation, how much is 1 standard deviation here? 1 unit only. From minus 1 to plus 1. What is the probability that? The probability that the random variable x takes values between minus 1 and 2 plus 1. How much is that? Minus 1 to plus 1. P of minus 1 less than x less than 1. What is the probability the random variable can take any value within 1 standard deviation of the mean? Mean is 0. 1 standard deviation on the other side is 1 unit. 1 standard deviation on the other side is minus 1. So what is the probability that the random variable takes any value within 1 standard deviation? It is 0.68 or 68% of the area of the curve. And what is the probability that it takes any value within 2 standard deviations on both sides? Within 2 standard deviations on both sides. Same thing that I've discussed in the previous slide, I'm repeating here with the different parameters or special case we have taken. Similarly, what is the probability that the random variable takes any value within 3 standard deviations on both sides? This is 99% of the area, right? 0.99 is the area of this curve from minus 3 to plus 3. So what is the height here? In the previous slide also I missed writing this. What is the height of the curve? There are some important details to observe here. What is the height here? It is 1 by root of 2 pi into sigma square. So this one at x equal to x bar. At x equal to x bar. If you substitute x with x bar minus x bar is 0. E bar 0 is 1. So whatever you are seeing here, that is the height of the curve. Similarly, what is the height here? It is 1 by root 2 pi sigma square, but sigma square is 1. If you put x equal to 0, at x equal to 0, we are having peak value. If you put x equal to 0, we get 1 by root 2 pi. Okay. Since the area of the curve should be 1, as standard deviation increases, height decreases. Correct or not? See? As standard deviation increases, what happens? The curve will become wider. The curve becomes wider. But as the curve becomes wider, area should still remain 1, because if it is PDF, area should remain 1. As the curve becomes wider, height should reduce so that the area will become 1. Because if the height does not reduce, only the width increases, area will increase. So that's why, see this one. As sigma square increases, width increases, it becomes wider. Because you can observe that outside also there is sigma square in the denominator. As sigma square increases, the height decreases, and width increases, and overall area remains to be 1 only. Okay, right, very good. So these are the details about a normalized Gaussian distribution function, same as the general Gaussian distribution function. So whatever we discussed here, same thing we are discussing here with special parameters where mean is 0 and variance is 1 unit. Okay, right. So in this, let me define what is Q function here. Okay, let me define what is Q function. Q function or F function means the CDF function based on this. CDF function based on this, how do we write it? CDF function means the definition of this is, let me first write the definition of CDF function. The meaning of this is P of probability that the random variable x takes a values less than or equal to small x. If this is x naught here. So capital F of x represents CDF function. CDF function means it is accumulation of all the probabilities till the value x, till the value of random variable taking x. So x less than or equal to x means here we are trying to find the probability of the random variable taking all the values less than or equal to x, or from minus infinity to small x, whatever is the probability that we are adding up. So that is the meaning of f of x. And how about q of x? Q of x meaning is just the opposite. Q function is always defined only on normalized Gaussian distribution, not on general Gaussian distribution. Okay, whatever Q function is defined, whenever you are talking about Q function is based on Gaussian distribution function with the mean 0 and variance as 1 unit. So the meaning of this is Q function is just the opposite. The meaning of Q function is exactly opposite of F function. Q function meaning is exactly opposite of CDF function. In F function, in CDF function, this is CDF function. In this, we are interested in the probability of random variable taking values from minus infinity to x. Okay, minus infinity to plus infinity. From minus infinity to x, we are interested in CDF function. In Q function, the remaining probability we are interested. The remaining probability, which is capital X greater than small x. We are interested in the probability of random variable taking values from x to infinity. From x to infinity. This total area is 1. We know that much. Only this part is like f of x, and this part is like q of x. Okay, this part is like q of x. So I'll take some value here. For example, I'll take x naught. Okay, this area from x naught to infinity, what do we call this? From x naught to, instead of x, I've taken x naught just for convenience, better understanding, because x is already the variable. No? So a particular value of the variable, instead of x, I'm taking it as x naught. Let me say it as x naught. Let us take it as x naught. It's not a big deal. Just to avoid confusion. Okay. So q of x naught means area from, or probability of random variable taking values from x naught to infinity. So add up the probability of x naught plus 0.1, x naught plus 0.1, all these probabilities. These are the probabilities. Just add up all the probabilities from x naught to infinity. This area in blue is the area that we are talking about here. P of x greater than x naught. P of x, random variable taking values greater than x naught. This is the area. What does it actually represent? It represents q function, q of x naught. Okay. So if you're talking about area from 1, it represents q of 1. If it represents area from 0, it is q of 0. It represents area from minus 1 to infinity, it is q of minus 1. So in general manner, I've talked about x naught. X naught is any value. From x naught to infinity, if you find the area of normalized Gaussian distribution function, that we call it as q of x naught. And this remaining area, observe this remaining area. The remaining area, see this one? This remaining area till x naught. This remaining area till x naught. What is it representing? This is representing the probability that the random variable takes values from minus infinity to x naught. This total area represents the capital F function or CDF function value at x naught. This total area represents CDF value at x naught, and this area represents CDF Q function value. So if you observe, if you add them up, f of x naught plus q of x naught, if you add it up, what is the result? F of x naught and q of x naught, if you add it up, what is the result? Anyone? F of x naught and q of x naught, if you add it up, the result is 1, correct? Because f of x naught represents this part of the area, q of x naught represents this part of the area. Together, both are covering the total area of the function. And the total area of this PDF function is 1. We know that much. So if you add f function and q functions values, the result will be 1. A very important result. So if you know f function value, you can find the q function value, correct? Can we write q function as 1 minus f function? Is that okay? Similarly, f function we can write as 1 minus q function. Very simple stuff, because total area is 1. If you know this area, if you subtract this area from 1, you get this area. Or if you subtract this area from 1, you get this area. Right? So that is the relation between q function and f function. Now let us understand a few more things as well. What is the relation between f of minus x naught and f of x naught. What is the relation between these two? And what is the relation between f of minus x naught and q of x naught? What is the relation? Let us understand this relation. So once you understand these relations, it's from graphical, we can understand these relations. We can easily understand these relations graphically. Focus carefully. When I say f of minus x naught, what do I mean? F means area from minus infinity to that point, right? X naught is here, means from 1 to 2, in between one point I've taken. Minus x naught means it is somewhere here, correct? Minus x naught is somewhere here. Observe carefully, observe carefully. So when I say f of minus x naught means I'm talking about this area. See this, see this, see this, this area, minus infinity to x naught, minus x naught. This area we are calling it as, whatever is in red, we are calling it as f of minus x naught. Observe this area and this area, because this symmetric curve is the area from minus infinity to x naught, minus x naught, same as area from x naught to infinity. See and tell me, is it same? Because it is symmetric curve, na? Whatever is the shape that you are seeing from minus infinity to minus x naught, same shape you are seeing from x naught to infinity also. Since it is a symmetric curve, this area which represents q of x naught and this area which represents f of minus x naught, both are same or not? So f of minus x naught is exactly same as q of x naught. Value wise, they are same. F of minus x naught is exactly same as q of x naught. And how about its relation? And how about its relation between f of x naught or minus x naught relation with f of x naught? How about its relation? Because we know that, just now we understood that f of minus x naught is same as q of x naught. Q of x naught we can write it as 1 minus f of x naught. So the relation is 1 minus f of x naught. Hope you're following. I want you to understand the relation between f of minus x naught with f of x naught and q of x naught. We've understood that f of minus x naught, this area is same as this area because it is a symmetric graph. So this area is same as this area, hence f of minus x naught is exactly same as q of x naught. Since these two are same, we know the relation between q of x naught and f of x naught. Q of x naught can be written as 1 minus f of x naught. So that is how we got the relation between f of minus x naught and q of x naught, f of minus x naught and f of x naught. Very simple stuff. Similarly, can you tell me how about q of minus x naught? Q of minus x naught, in the similar manner you can understand, no? Q of minus x naught, see this one, if you replace x naught with minus x naught, you replace x naught with minus x naught, you can understand that q of minus x naught is same as f of x naught. And f of x naught can be written as 1 minus q of x naught. See this? Very simple stuff. So f of x naught can be converted in terms of f of minus x naught. Q of x naught can be converted in terms of q of minus x naught. Similarly, so there we can play around with the q function and f function. Why? Because in the options, when they ask you a question, for example, they say f of 1. In the options, you got f of 1 as answer. Okay. In the options, you may not find f of 1. F of 1 is also same as 1 minus f of minus 1, correct? According to this relation. Okay, according to this relation, f of 1 is same as 1 minus f of minus 1, correct? You might find this in the options instead of this. Or it is also same as q of minus 1. You might find this also in the options. Or you might also find 1 minus q of 1 in the options. Any of these three, instead of this, you can find any of these three in the options. So all the four are representing the same answer. So once you solve a question based on Gaussian distribution function, your answer will be in the form of q function or f function. The result that you get will be in the form of q function or f function, something like this. But in the options, you may not find the exact thing that you got. It can be different because they can be represented differently using these relations. So these relations are very, very important stuff. Okay. I hope it is clear. So this is little tricky stuff, definitely. This is little tricky stuff. Even for me to master it also, I've taken quite some time to master it. So you guys, if you want to master it, if you want to be confident of this topic, you have to learn it carefully. Okay, very carefully you have to learn it. So after the session, you try to plot it, and whatever things I have taught you, whatever things I have derived, you try to do it on your own. You try to derive them on your own. You try to write all those relations on your own. Once you write them, then you'll get the confidence. If you're not confident of any particular thing, just go through the class again. Okay, if you are not confident of particular part, just go through that part of the class again and again till you get the confidence. This topic is tricky, but once you understand, you will admire it. So that is the beauty of Gaussian distribution. You mean Q function? Sure, we can explain. See, I have explained about f function and q function. F function means area from minus infinity to x naught. Area from minus infinity to x naught, this total area, we call it as f of x naught. Similarly, q function is just the opposite of it. In f function, we find the area from minus infinity to that point. In q function, we find the area from that point to infinity. Okay, so q function means area from that point, whatever is inside, whatever is the argument inside the q function, from that point till infinity, whatever is the area, that we call it as q function. F function means area from minus infinity to whatever is the argument. Till this point, we find the area. So in q function, we find the area from that point, In f function, we find the area till that point. Okay, next, f of minus x naught, the meaning of f function is same. We want to find the area till that point. So what is the, till that point? Till minus x naught, you're going to find the area. So this area, f of minus x naught means your f function means you are going to find the area till that point. From minus infinity till that point, you find the area. This is my f of minus x naught. This is f of minus x naught. So in q function, if you observe q of x naught, if you see the area from x naught to infinity, whatever is the area. See this one? The graph, whatever is the shape that you see here, exactly same shape on this side also. Because it is symmetric graph, whatever is the area here, same will be the area here. From that observation, we can say that f of minus x naught is same as q of x naught. F of minus x naught is same as q of x naught. And we know that q of x naught is equal to 1 minus f of x naught. Q of x naught is equal to 1 minus f of x naught. We know that because when you add them, the total area is 1. So q of x naught can be written as 1 minus f of x naught. So from that, I have written this. Using the same basics, instead of f of x naught, how about q of minus x naught? Q of minus x naught, if you want q of minus x naught, see this one? Using this relation, instead of x naught, replace x naught with minus x naught. Replace x naught with minus x naught on both sides. What happens? Q of minus x naught is equal to f of minus x naught, which is f of x naught. That is what I've written here. From this relation, I've written this. Graphically also you can understand that. And from this, f of x naught I have replaced with 1 minus of q of x naught. That is how I got these relations. So if you want, you can understand this graphically also. Q of minus x naught means what? Q of minus x naught means area from minus x naught. From minus x naught till infinity, whatever is the area. From this point till this total area is what we can call as q of minus x naught. And this area, just keep this in mind, this area is same as this area. Correct on, because it is symmetric graph. From minus infinity to x naught, whatever is the area, same is the area from minus x naught to infinity. This is f of x naught and this is q of minus x naught. Both are same. Okay, observe on the curve. Okay, observe on the curve. It will be very easy to understand. Every relation that we have written here, everything can be understood graphically. Spend some time, you will be able to understand. Okay, this is not straightforward stuff. This is little tricky stuff. But once understood, then you will never forget it, or you'll never have a misunderstanding. Okay. Fine. That is the story of normalized Gaussian distribution function. And how about the relation between a general Gaussian distribution function and normalized Gaussian distribution function? Let's establish the relation between them. Fx of x represents a general Gaussian distribution function where the mean can be anything, variance can be anything. Okay. And f of x represents a normalized Gaussian distribution function where variance is 1. I'm substituting variance as 1. This is a special case of this. E power minus, mean is 0, variance is 1, it becomes e power minus x square divided by 2. Okay. Now, how about what is the relation between these two? What is the relation between these two? So from this, what I'll do is I will substitute in this function, normalized Gaussian function, I'll substitute x with x minus x bar divided by sigma. See this? I'm replacing x with x minus x bar by sigma so that I get a function which is similar to this. Now this will be 1 by root 2 pi into e power minus of x minus x bar whole square divided by 2 sigma square. See this? I've substituted x with x minus x bar by sigma. X minus x bar by sigma whole square, which is same as x minus x bar whole square by sigma square. See this? Yeah, are these two same? No, not exactly same. They are not exactly same. The difference is fx of x is equal to, there is only sigma square that is different. Sigma square is missing. Under root, it is sigma square. So this function, when you divide it with sigma or divide it with root of sigma square, that is when you get this function. So it is f of x minus x bar divided by sigma. This function, you just divide it with sigma. You just divide it with sigma. This function, once you divide it with sigma, this will be exactly same as this function. So this is the relation between, this is Gaussian function with mean x bar and variance sigma square, and here f function represents a normal distribution with mean 0 and variance 1. This is normal distribution with the mean 0 and variance 1, whereas this is Gaussian distribution function with any mean x bar and variance, any variance sigma square. So I am trying to establish relation between two Gaussian functions. One is with any mean and any variance, another one with mean 0 mean and variance is 1 unit. So this is the relation. Now let's integrate on both sides. Once you integrate, what happens? Once you integrate from minus infinity to x, what happens? You get CDF. PDF becomes CDF. So PDF becomes CDF. So small fx of x becomes capital Fx of x. On the other side, it becomes 1 by sigma into small f of becomes PDF becomes CDF. PDF becomes CDF. What are we doing here? We are integrating on both sides. When you integrate, PDF becomes CDF. This PDF also becomes CDF, but there is inside x is divided by sigma. So when you integrate, what happens? When you integrate, in the denominator you'll have 1 by sigma. See this? Because x is divided with sigma, when you integrate, what happens? Integration of x by sigma, if you have, so when you integrate, what happens? That 1 by sigma will be divided, no, inside the function. I hope you are well aware of it. For example, f of ax, if you differentiate, what happens? D by dx of f of ax is f dash of ax into a, something like that. Similarly, if you integrate this, what happens? You will do integration of this, and since the variable is multiplied with a, if you integrate, it will be divided by that constant, right? In the same manner, so here the variable is divided with sigma. So if you are doing differentiation, that 1 by sigma will be multiplied. Since it is integration, it will be divided with 1 by sigma. And this function integration, we know it is capital F, which represents CDF. Okay. So there are different ways in which we can establish this relation. Generally, I teach in a different manner in regular classes. So today I am trying to explain in a much more easier manner using basic integration differentiation stuff. So this 1 by sigma cancel. So this is the relation fx of x or x naught. Instead of x, I am putting x naught just to avoid confusion. It is f of x naught minus x bar divided by sigma. So this is the beautiful relation between CDF of any Gaussian function in relation with CDF of normalized Gaussian. Why do we need this relation? Because these values are available. So CDF values f of 1, f of 0.5, f of 1.6, 0.7, 0.8. These values are available in our textbooks, or this data is available. Why is this data made available? Because Gaussian function, especially in all communication textbooks, at the end of the textbooks, you'll have appendix. In that, you'll definitely have these values, f function values or q function values available at the end of the textbook. Why? Because in many problems in communication systems, we'll have noise topics. In noise, because noise is Gaussian, for a Gaussian function, because it is a complicated curve, right? See this one? This is a complicated curve. If you want to find the area from, let's say, 0.9 to 0.8, can you find it easily? No, it's very tough. By doing integration, mathematical integration, and finding the area from 0.8 to 0.9 to 0.8, or 0 to 0.5, or 0.5 to 1.5, something like that, it's very tough. Correct or not? Because see this one, it is having e power minus x square kind of equation, which is very difficult to integrate. So that's why these values, using some methods, they found all the values, and they're making available as those values which we can access. But for every Gaussian function, if they want to provide, that is not possible, no? Because Gaussian function can have any mean and any variance. They can't provide these capital F function or CDF function values for every possible mean and every possible variance. That's why what they do is they provide these CDF function values or Q function values only for a normalized Gaussian distribution function. So whatever is the distribution that you are dealing, whatever is the Gaussian distribution you are dealing with, any mean, any variance, if you can convert that using normalized Gaussian function, yes, you can take we can access these values. In any problem that will be asked based on Gaussian function, generally the answers will be based on this function, which is a normalized Gaussian function. So whatever answer you get, you can convert into this form. Okay, what do I mean by this? Let me explain. I'll take an example problem and then I'll explain. A random variable x has mean 10 units and variance 4 units. Okay, now find, the questions will be something like this. Find P of x greater than P of x greater than 12, for example. Okay, so P of x greater than 12, always try to express it in terms of CDF. So CDF means x less than, it should be in the format of x less than. So without changing its value, let us write it as 1 minus P of x less than or equal to 12. Can we write it like this? So x less than or equal to 12 means, can I write it as 1 minus CDF function value at 12? This is the CDF function value at 12. But this CDF function value, let us convert it using the relation that we have established. Let me write that relation. Fx of x can be written as f of x minus x bar divided by sigma. See this? So instead of fx of 12 here, let us write it as f of 12 minus, what is the mean value of this function? Mean value is 10, variance is 4. Here sigma means standard deviation. What is standard deviation here? Variance is 4 means standard deviation is 2. So 12 minus x bar is, subtract the mean, which is 10 units, and divide with standard deviation, which is again 2 units. So this is equal to 1 minus f of 12 minus 10 is 2, 2 divided by 2 is 1. 1 minus f of 1. And you can leave it at this place. And we know 1 minus f of x naught is same as q of x naught, which is q of 1. 1 minus f of x is q of x. Or we can also write it as f of minus 1 also, because q of x naught is same as f of minus x naught, right? You can write it that way also. Or we can also write as 1 minus q of minus 1 also, because f of min same as q of minus 1. So that way we can write it this way. So there are 4 different ways in which you can write the answer. In the options, you might find one of these 4. Next, similarly, second question, P of x less than or equal to 14. How about this one? It is looking like fx of 14, but this will not be available in the options. So answer is available in terms of CDF or Q function of normalized Gaussian. It is capital F of, so 14, subtract the mean from it and divide with standard deviation. I'm just using this basic, using this relation only. So which is f of 4 by 2, which is a capital F of 2. Next, one more, just for understanding sake, P of 8 less than x less than or equal to 10. How about this one? Can we write it as, write it in terms of CDF? We can write it as P of x less than or equal to 10 minus P of x less than or equal to 8. See this? From 8 to 10. Find the probability till 10. Find the probability till 8. If you subtract, you will get the probability from 8 to 10. Now, this is looking like fx of 10 minus this is looking like fx of 8. And fx of 10, let's convert it using CDF of normalized Gaussian. It is f of 10 minus 10, correct? 10 minus 10 divided by 0, 10 minus 10 divided by sigma is 2, minus f of 8 minus 10 divided by 2. This is f of 10 minus 10 is 0, which is f of 0, minus f of minus 2 by 2 is minus 1. How much is f of 0? Anyone? How much is f of 0? F of 0 means what? In a normalized Gaussian distribution function, f of 0 means area till 0. What is the area till 0? The total area is 1. We know that much. And we know that it is symmetric. So whatever is the area till 0, same is the area from 0 to infinity also. How much is that area? What is f of 0? F of 0 means area from minus infinity to 0. How much is that? Total area is 1. The half of that area is half only. It is also same as q of 0. Very simple stuff. Q function area. Q of 0 means area from 0 to infinity. Area from 0 to infinity is also half. Okay. Right. Let's move on to the topic. F of 0, we know that it is half minus f of minus 1. How do we write it in other ways? Half minus f of minus 1 can be written as q of 1, correct? F of minus 1 can be written as q of 1, or the other ways of writing it is half minus f of minus 1 can be written as 1 minus f of 1, correct? And half minus f of, you can write as f of minus 1, you can replace it with q of 1. 1, 2, 3 answers we are done. So we can also express it in terms of q of minus 1 also. Q of minus 1 also, which we can write as 1 minus q of minus 1. F of 1 can be replaced with q of minus 1. So there are 4 ways of representing the same answer. Okay. So like this, we can solve questions based on Gaussian random variables. The only 2 important parameters about Gaussian random variable are mean and variance. Only these 2 parameters. Using those 2 parameters, you can plot it. You can find everything that we want to find. Right. So that is the discussion about Gaussian random variable. I have covered almost all the details based on Gaussian distribution function. So if you have any confusion, just it's worth going through the class again. So because I've covered lots and lots of points, which will be very helpful for you guys in multiple situations. Right. So go through the session again if you feel like going through it. If you feel like you have some more points to observe, it's better you go through the session again. Right. And I have given you some homework questions as well. So I've given you some easy homework questions here. So if you're able to solve the questions and if you're confident of your answers, post it in the comment section. Okay. And don't forget to subscribe to the channel if you have not subscribed already. And don't forget to press the like button if you liked the content that I've provided. Okay. So that's it, guys, from my side. In tomorrow's session, we will talk about the same manner that we've talked about Gaussian random variable. We'll talk about exponential random variable and uniform random variable, which means I'll be talking about exponential probability density function and uniform probability density function. We'll talk about all the details about that function, those 2 functions. Okay. In tomorrow's session, we'll talk about exponential distribution and uniform distribution. And in day after tomorrow's session, I'll discuss multiple different types of problems based on all the topics that I have discussed in this week. So based on PDF, CDF, moments, Gaussian random variable, exponential, uniform, all those topics, I'll be discussing questions based on them in day after tomorrow's topic on Sunday, 8 a.m. Gokulan, you just go through the channel, na? Just browse through the channel, you'll get it. Okay, or else you can you have my Telegram channel link, right? Yeah, this is my Telegram channel, Telegram group. So all the links generally I post it in that group. Okay, I'll share the PDF also. I'll share this PDF also in that group, so you can access it. Okay. In the YouTube channel itself, just browse through them or just search with my name. Just search the classes with my name, or just in the channel, go to the channel and just go to videos section, like home. After home, that videos option will be there. Now, once you go to the channel, just browse through. You'll get the last videos that I've taken. You can easily get them. The first class is on probability density function. Second class is on cumulative distribution function. Third is moments of random variable. The fourth class I have taken today, which is Gaussian random variable. You can search with the exact name or just browse through the videos. You'll easily get it. Okay. Fine, then we'll stop at this place. So have a nice day. Take care. Bye bye.